Hello, everybody. Welcome to, learning of calculus with me. Today we will be talking about implicit differentiation. So this is going to be after talking about product rule, quotient rule, and chain rule as well. So those are the topics that we covered as of right now. So the question is then, what is implicit differentiation and how do we actually use it? So that's basically kind of like the first question before we go into anything else. Implicit differentiation, the best way I can describe it is that whenever you have to solve for a derivative, a lot of times, majority of times so far anyways, it's going to be a function of y, meaning that you can get y all by itself. But what if you cannot solve for y all by itself? What if that function, or what if that equation is not a function, but instead a relation? So for example, maybe if we have, say an equation of a circle, and what I want to do is I want to find out what is the equation of the tangent line at a certain point. So maybe say for example at 3 comma 4. So you can see the idea here is that, well, if I want to do that, I probably need to solve for y and then afterward take the derivative and then afterward find out what is then the point of the tangency. And we can actually do that though. So over here, we'll go ahead and do so. Y is supposed to be equal to the square root of 25 minus x squared. And technically, yes, there is a plus or minus, but because the point that we're choosing right now is in quadrant 1, we'll go ahead and negate the negative part. And for now, we'll go ahead and solve for y prime. Y prime, according to my power rule and also chain rule, is going to be 1/2 and then the square root of 25 minus x squared in the denominator. And according to the chain rule, there should be a negative 2x on the top because that's the derivative of 25 minus x squared. Now we can go ahead and cancel out, and then we can go ahead and plug in the point, which is 3 comma 4, and that will give us the answer then. So the derivative or the tangent, the point of tangency, what is the slope there is going to be the following. 3 we plug in, and then divided by the square root of 25 minus 16, which looks like it's going to be equal to 9, is that right? No, 25 minus 9, so that's going to be square root of 16, so the answer is equal to 3/4. So you can see the procedure is not that bad, I suppose, if you want to solve for the derivative and then afterwards plug in and all that stuff. But implicit differentiation says, hey, you know what? We don't have to actually worry about having to do all of this stuff. Instead, what we can do is just take the derivative from the very get-go and you don't have to solve for y. So the question is then, how do you actually do it then? So for the same problem, let's go ahead and write it again. So I want to find out what is the slope of the tangent at x is equal to 3 and y is equal to 4. So here graphically, I'm just going to go ahead and draw that on the side. You have a circle which is going to be centered at 0, 0, and then you have a point up here which is going to be 3, 4. And what I'd like to do is I would like to find out what is the slope over there. So according to implicit differentiation, it basically says you can just go ahead and take the derivative as is. But just keep in mind that when you take the derivative with respect to y, because of what we did earlier, how we can solve for y, you have to treat y basically as a function. And that's where chain rule is going to come in. So here's what's going to happen then. So first, I'm going to go ahead and write d dx to implement that I'm taking the derivative then. The first part for the derivative of x squared, that is just going to be equal to 2x. And then the derivative of y squared, now if you think of it as just like regular taking the derivative, you would think, okay, well, the answer is going to be 2y. But this is the part that's special according to implicit differentiation. So because you're taking the derivative with respect to y and not with respect to x, then you can think of it as this way. Since y is a function of x, then there's a chain rule. So that means that you multiply by dy dx, and that's where the derivative is going to appear then. Now, as for the derivative of 25, well, that's just going to be equal to 0 because that's a constant then. This equation, we can go ahead and still solve for dy dx, or y prime, whatever you want to call it. I noticed that the 2's, we can go ahead and cancel those out too. And remember, we're just going to plug in 3 and 4 in this case then. So it's going to be 3 over here, and then plus 4, and then multiply by dy dx is equal to 0. So the derivative is going to be equal to, looks like it's going to be negative 3 over 4. So going back to this problem that I just did earlier, and I noticed I made a small mistake because there's a negative and negative right here, you can see how the two problems, it gives you the same answer, but by using implicit differentiation, it's a lot faster because you don't have to solve for y. So let's go ahead and see if we can do that or apply the implicit differentiation for other stuff just to make it a little bit easier too. So here's an example. Find the equation of the tangent line for the sine of y minus cosine of xy is equal to x minus y at x is equal to -1, comma y is equal to 0. The graph of this, I don't even want to know what that looks like, but I guess in a way, for curiosity's sake, we can go ahead and just show it just in case. Let's see if I can actually go ahead and plug that in though. Oh, sorry, don't remember my equation. So sine of y minus cosine of y. So let's see here. So sine of y minus the cosine of xy. And then that is going to be equal to, I believe it was x minus y. So let's see if that is going to be it. Yes, and you can see that this graph right here is definitely not a function. And trying to solve for what y is equal to just strictly is going to be impossible in this case. So instead of having to solve for y, then we just go ahead and implement this implicit differentiation then. Okay, so let's go through the procedure. First, I'm going to go ahead and just write d dx to imply that I'm taking the derivative of the entire equation. So the only thing that you have to keep in mind is that you just take the derivative as you would normally. But anytime you have to take the derivative with respect to y, that's where you're going to write y prime because of the chain rule. So the first part, sine of y, the derivative of sine, that's going to be cosine of y. And right there, that's where you're going to see y prime then, because remember, the derivative of y, that's where y prime is, okay? Minus the second part. Now this one, that's going to be a little bit tricky because you have cosine of x times y. And what that means is you have a chain rule, that's number one, and also a product rule because there's a chain rule inside. So let me just go ahead and take it one step at a time. The derivative of cosine, that is supposed to be sine negative. So that's going to be plus and then x times y multiplied by the derivative of xy, x times y prime. Now that part I'm going to go ahead and use the product rule for, so we can kind of show that in just a little bit. But for right now, I'm just going to kind of like show the work step by step so you can kind of follow along. For the next part, the right side of the equation, the derivative of x is just equal to 1 minus the derivative of y, again, that's going to be just y prime. So technically, you can say the derivative of y is going to be 1 and then multiply by y prime because of the chain rule. So that's what it's supposed to be. Let's go ahead and clean this up a little bit more. So cosine of y multiplied by y prime plus sine of x times y multiplied by the derivative of that thing right there according to the product rule. So this part you have to watch out for. So the product rule says that it's going to be the second equation multiplied by the derivative of the first, and then plus the first equation multiplied by the derivative of the second. And then all that is now equal to the right-hand side once again. So 1 minus y prime then. And remember, the objective here is to find out what is the equation of the tangent line. So you have two things that you can do. You can either A, solve for y prime, or B, you can go ahead and plug in -1 comma 0 right now. I personally think it's a lot easier to just go ahead and plug it in. So let's go ahead and do that then. So on the left, I'm going to go ahead and plug in the point then. So here, let me just go ahead and indicate that. -1 comma 0 plugged in. You are going to get, according to this, cosine of 0, which is equal to 1, multiplied by y prime. And then plus sine of, looks like it's 0, so all that is going to be equal to 0, so that's kind of nice. And all that is equal to 1 minus y prime once again. So then we're going to go ahead and solve for y prime, and looks like in this case, we're going to go ahead and move the y prime over to the left. So 2y prime is equal to 1. So y prime, meaning the slope over there at -1 comma 0, is going to be equal to 1/2. Okay, so that's probably the fastest way. Now, just for curiosity's sake, what I'm going to do is I'm going to go ahead and take this equation that I get after I use implicit differentiation, and I'm going to go ahead and solve for y prime because sometimes I want to solve for y prime, because that's what the problem is asking for. So let's go ahead and clean that up then, okay? The only thing I can see that we can do algebraically is on the left-hand side, we can take this guy over here and multiply everything out. So let's see, cosine of y multiplied by y prime, and then plus, looks like it's sine of xy multiplied by y, and then we also have xy prime multiplied by the sine of xy. And all that is equal to 1 minus y prime. Remember, take all the terms that contains y prime and isolate them. So let me just go ahead and underneath them for the time, underline them for right now. So that's this one, and then that's this one, and then that's this one. Okay, so everything you see with y prime, we'll go ahead and put on one side. Everything that does not have it, we'll put on the other side. So algebraically, let's go ahead and keep them on the left-hand side. Let's see, we have cosine of y, and then plus x multiplied by the sine of xy, and then we have plus 1, and then we're going to take out the y prime that they all have in common, okay? And all that is equal to, now anything that does not have y prime, we're going to go ahead and move over to the right then. So I'm going to use double line for that one. So 1 minus y multiplied by the sine of xy. And finally, to get y prime all by itself, then we're going to go ahead and divide through. So y prime is equal to 1 minus y multiplied by the sine of xy, and then all divided by that big nasty factor right there. So cosine of y, and then plus x times the sine of xy, and then plus 1. Okay? So again, if you want to solve for y prime, you're going to go take the path on the right. But if you want to solve for what is the slope by plugging in the numerical value, you probably want to take the path that's on the left. Okay? Never take the path that's on the right to solve for y prime and then use that equation at the very end to solve for the slope, because that actually just takes a very long time and it's not very, I guess, a wise way of going at it because it's not very time efficient. Okay, let's try a different one, or let's try something else with the implicit differentiation. Let's say this time around I want to find the second derivative of this equation at 1, 1. Now, let's see. Let me go ahead and check, make sure everything is okay. And I noticed that I am not going to get something, well, actually, this is kind of strange, and I guess this is a small little technicality, but it does matter. 1, 1, according to this, I actually can't plug in because it doesn't work, because you get 1 minus 1 is equal to 2. So let me just go ahead and change that equation then to x to the 4th plus y squared is equal to 2, then is equal to 1, 1. By the way, this is actually a good thing to always try to check for in the future, just to make sure that the point actually exists on the curve that you're trying to find the tangent for, because otherwise it would not make any sense if you just plug in anything that you want. All right, but anyhow, going back to what I was saying, I'm going to go ahead and find the second derivative for this equation. So again, we'll go ahead and apply to the implicit differentiation. So hopefully by now I don't have to write the dx part, but you can go ahead and follow along. So the derivative, going for the first derivative anyways, we're going to get the following. 4x cubed, and then plus 2y, and then that's where y prime comes from, and all that is equal to 0. Okay, so again, as you can see, taking the derivative with respect to x, for the x part, it's just as is, but for the y part, that's where the y prime comes in. Now, what I'll do is I'll go ahead and isolate y prime because I want to solve for that before I solve for the second derivative. Let's go ahead and also divide by the 2 that they all have in common then. So let's see, we have 2 multiplied by x cubed, and then that is going to be equal to, or sorry, let's just say plus y prime is equal to 0. Okay, so let's see, keep cleaning it up. Then we have y prime is equal to negative 2x cubed. And so y prime, the derivative, is going to be equal to negative 2x cubed, and then all divided by y. So that's going to be my first derivative. Okay. At this point, what we want to do is I want to solve for the second derivative. So you can go ahead and take what we have right there and take the derivative according to whatever rule that we have. In this case, I think the quotient rule is what's going to be called for. So let's go ahead and do that. Okay, so let me go ahead and take this guy right here and solve for the derivative using quotient rule. So y double prime, that is going to be equal to, well, according to the quotient rule, here's what we're going to get then. Let me go ahead and factor out the -2 because the constant, I think that should just carry over and that'll make things a lot easier. So according to the quotient rule, it's going to be the bottom equation multiplied by the derivative of the top minus the top equation multiplied by the derivative of the bottom. And again, you see where the derivative of the bottom y is supposed to be y prime. So that's where that's coming from. All divided by the bottom squared. So y squared then. Okay. Okay, so let's see. So what we have now, we can just go ahead and clean up as much as possible. One thing that you should kind of consider also is that, hey, if you notice, you have y double prime, the derivative that you're looking for, which again, we can denote as d squared y divided by dx squared. There's a y prime right there. There's a y prime right there. So the question is, well, how do you get rid of it? Or how do you kind of like make it look a little bit prettier? Well, the answer to that is just right on top, because you can make a direct substitution for y prime. So my final answer, or my, somewhat substituted answer, will be the following then. -2 multiplied by 3x squared y minus x cubed multiplied by y prime, that gets replaced by -2x cubed divided by y, and then finally all of that divided by y squared. And I guess if I want to make this a little bit nicer, we can go ahead and take all of this and multiply everything by y just to get rid of that smaller fraction. So I guess my cleaned up form would then be -2 multiplied by 3x squared y squared, and then we have plus 2x to the 6 and all divided by y squared. Okay, so that will be our second derivative. Now, according to my last problem, some of you guys might be wondering, well, is it possible for me to actually take the second step right here and just take the derivative again using implicit differentiation? And the question and the answer to that is yes. You're most likely going to be able to get the same thing as what you have on the that I have on the bottom if you solve for y double prime then. Okay, so if you want, you can go ahead and give it a shot. This is a preference thing because, if you want to take the derivative on the second step using implicit and it's easier for you, that's go ahead. But the traditional way is basically doing what I did, which is to solve for y prime and then afterwards solve for y double prime. So, you take your pick and figure out what works best for you. Okay. The next piece of the implicit differentiation, like what is it for and how do we actually use it for something that's important? Well, this is the part right here. What I want to do now is I want to solve for the derivative of trig inverse function. So meaning what's the derivative of sine inverse of x? What's this derivative of cosine inverse of x? And so on and so on and so on. Now keep in mind, from back in trig, when I say sine inverse of x, that does not mean 1 over the sine of x. The reciprocal and the inverse for trig functions, they're completely different. They're not exactly the same thing. So just keep that in mind. Just remember, this guy right here, what I'm trying to solve for, is going to be an angle or in some sort of radian. But whereas this guy right here, 1 over sine, that is going to be a ratio. So they're two totally different representations. But nonetheless, what I want to do is I want to solve for the derivative of sine inverse of x, okay? So not cosecant of x. So let's go ahead and do that. And let me go ahead and erase what we have over here so you can see how that actually works out. So let me go ahead and use a bigger eraser. Okay, so here we go. So first what I'll do is I'm going to go ahead and say y is equal to sine inverse of x, just so that we can just introduce another variable so we can utilize implicit differentiation. First, what I'll do is I'll take this equation and I'm going to go ahead and take the sine of both sides because I don't know what to do with the sine inverse. So we'll go ahead and write it as sine of y is equal to x. And now we can go ahead and use implicit differentiation to solve for what is a derivative then. So according to what we have, the derivative is going to be the cosine of y multiplied by y prime, which is what I'm trying to solve for, is equal to 1 because that's the derivative of x. Trying to isolate y prime, now I'm going to have y prime is equal to 1 over the cosine of y. Now, according to what we did earlier, we're most likely going to be done at this point, but we're really not actually. There is kind of like an unwritten rule where it says that if your function starts as y is equal to a function of x, you actually have to solve for the derivative strictly in terms of x. So what that means is I actually don't want this cosine of y. I actually want to change it so that it's in terms of x. So then that way it'll be, well, according to what we just said earlier, right? Everything is in terms of x because we start off with y is equal to a function in terms of x. So the question is, how do we change that cosine of y? And this is where we have to do a little bit of trig on the side then just to figure it out. Let's go back to that second step over there where we have sine of y is equal to 1 over sine of y is equal to x. We're going to go ahead and draw a right triangle, and this is hopefully somewhat familiar to you back from trig from last year. So what we'll say is that y, the angle, is going to be over here. And according to trig, right, sine of y is equal to x. Well, that's saying that the opposite side is equal to x, and the hypotenuse is equal to 1 because I can write this as x over 1. And that now allows us to solve for the missing side, which is this guy over here, which is 1 minus x squared. And the reason why that's important is now in that triangle, we can figure out what is the cosine of y. The cosine of y is adjacent over hypotenuse. So the adjacent over hypotenuse, then that's going to give us the square root of 1 minus x squared all over 1. And that's how we're going to figure out what that piece is then. So my final answer to this, y prime, is going to be equal to 1 over the square root of x 1 minus x squared. And that's going to be our derivative of sine inverse of x then. Okay, so a little bit tricky, but hopefully you can understand where that's coming from. Let's go ahead and try one more just so that you can get hopefully a better grasp of this. So now let's say I want to solve for the derivative of cosecant inverse of x. And again, just as I said in the last video, if you want to pause the video and try this on your own, feel free to, because I would definitely encourage it just so that you can see how far you can go without me here. Okay, so here we go. Let me go ahead and write it on the side or below it. So first we'll start by saying y is equal to cosecant inverse of x. So cosecant of y is equal to x. And then now I'm going to go ahead and take the derivative using implicit differentiation. So the derivative of this equation, we're going to get cosecant of y multiplied by the cotangent of y multiplied by y prime. And I do believe that is also negative, and that's equal to 1. Okay, move everything that's not y prime over to the right-hand side via division. So y prime is equal to 1 over cosecant of y multiplied by cotangent of y, and there's also the negative. I'm going to go ahead and put it over there too. And just to make it a little bit nicer looking, because I notice I have a lot of cofunctions and they're all under the reciprocal, this is the same thing as negative sine of y, because the reciprocal of cosecant is just sine, and then multiply by the tangent of y then, because the reciprocal of cotangent is tangent just itself. Okay, now that we clean that up, let's go ahead and create that right triangle just like we did before, because again, we don't want sine of y, we don't want tangent of y, we want y prime to be strictly in terms of x, because that's what we started with, a function of x at the very beginning. So on the side, I'm going to go ahead and draw the triangle. Okay, so the triangle is located right here, and according to the triangle, we're going to build it according to my step number 2 over here, right? We have cosecant of y is equal to x. So if it helps you see it a little bit better, then that means the sine of y is equal to 1 over x. That tells me y is this angle over here. You could use the top angle if you want, but it doesn't matter. Sine is going to be the opposite, which is 1, over the hypotenuse, which is going to be x. Now, if I want to solve for the missing side, then I'm going to use a Pythagorean theorem. So that's going to be the square root of x squared minus 1 then. So now we're going to go ahead and plug everything in according to what we see. First, according to this triangle, we can say that the sine of y is equal to 1 over x, because that's what we solved for earlier, right? That's one of those things we want to solve for. And the other thing that I want to solve for is tangent of y, because that's part of my derivative equation. And tangent, that's supposed to be the opposite over the adjacent. So that's going to be 1 divided by the square root of x squared minus 1. So taking my two parts and putting it all together, then y prime, the derivative, what I'm looking for, the derivative specifically of cosecant inverse, is going to be negative 1 divided by x multiplied by the x squared minus 1. So that right there is going to be my derivative of cosecant inverse of x. Okay. Now, for these type of functions, I remember when I was younger and I was taking calculus, my professor, or actually my teacher in high school, she basically told me, hey, these trig inverse derivative, it's up to you. If you want to memorize them, great. If you want to derive them every time for yourself, that's great too. The derivation is actually not that bad because you can see how it actually works. The memorization, you would think, okay, well, there's a lot to memorize because there are 6 equations, but it turns out that it's actually not too bad because there's really only 3. Now, just to give them to you, so then that way you can try it on your own, and also so that we can save a little bit of time, the derivative of sine inverse is supposed to be 1 over the square root of 1 minus x squared, and that one we just proved earlier. The derivative of cosine inverse is supposed to be negative 1 over the square root of 1 minus x squared. And that right there, you can kind of see what I mean by when I say it's actually not too bad, because you'll notice that the derivative of sine inverse is just the negative of the derivative of cosine inverse. So they're kind of like, if you can memorize one, you can memorize the other. For tangent inverse, the derivative is supposed to be 1 plus x squared. 1 divided by 1 plus x squared, whereas for cotangent is negative 1 over 1 plus x squared. So again, same idea. You can see that these two right here are kind of identical, where the derivative are just the negative of each other. And then for these two guys, they can be grouped also the same thing, so making the memorization a lot easier. For cosecant and secant, well, I derived one, so you can probably imagine what the other one's going to be then. So for cosecant, our derivation says that it's supposed to be negative 1 over x multiplied by the square root of x squared minus 1. So you can guess that the secant one is supposed to be the negative of that, which is 1 over x times the square root of x squared plus minus 1 then. So here, if you can just remember them by grouping, I think that'll make things a lot easier. Okay. But nonetheless, let's go ahead and take a look at the last few examples, and then afterwards, I think that'll probably do it then. So the next one is find the derivative of this function then. So y is equal to x squared multiplied by sine inverse of x. So we're going to go ahead and solve for the derivative, and we don't have to use implicit differentiation because, well, we don't have x and y on the same side. So we could just go ahead and take the derivative as is. So let's see, y prime, that is going to be, do you notice that we have two functions multiplied to each other? So that means that's where the product rule comes in. So product rule says, let's go ahead and take the second equation, multiply by the derivative of the first, so that's going to be 2x, and then plus the first equation, multiply by the derivative of the second. Now the derivative of sine inverse, we have that already, we derived it already, so that's going to be 1 over the square root of 1 minus x squared. So normally I'll just go ahead and say leave it at that. So it's really up to you or your textbooks depending on what they want. If you can leave your answer as is, then that's totally fine because you technically have the derivative. But if it's the case where your professor or your textbook says, hey, rationalize it so they're the same denominator, you might want to go ahead and do so then. Okay. But for me, normally this will be good enough. Okay. All right. So let's take one last example of this. Okay. Something a little bit more difficult. Again, what I want to do is I want to take this equation and I want to find out what is the slope of the tangent at the point 0, 0. So we can go ahead and try to do this together then. Okay. Now again, I don't know what the graph of this looks like. If you want to graph it, that's totally fine. Earlier on Desmos, I graphed it and it supposedly looks something like this then, which is basically kind of like a circle. So you can see that the derivative is supposed to be a horizontal line, so that tells me the derivative is most likely going to be 0. But again, you don't need the graph, so don't have to worry about that if you don't know what I'm talking about. Nonetheless, let's go through the procedure. Okay. We're going to take the derivative using implicit differentiation because we notice that x and y are on the same side. Don't ever try to solve for y if you don't need to, okay? So the derivative using implicit differentiation, the derivative of ln. Now the derivative of ln, we said we derived in the last section. Derivative, let me just go ahead and write on top. The derivative of ln of x is supposed to be 1 over x. So that means the derivative of this whole thing is going to be 1 over that whole thing, because remember, you're just thinking about taking the derivative of ln. Next, this is where the chain rule comes in. So multiply by the derivative of the inner function. The derivative of the inner function is going to be 2x plus 2y multiplied by y prime plus 0 is equal to. So remember, implicit differentiation for the inside part, right? So that's where the 2x comes from, 2y comes from, y prime, because you're taking the derivative with respect to y. On the right-hand side, the derivative of tan inverse, so that's going to be 1 over 1 plus y squared multiplied by y prime, because again, taking the derivative with respect to y, and also using the trig inverse that we derived earlier. Now, remember what I said also? You can either A, solve for y prime and then afterward plug it in, or B, you can go ahead and plug it in right now and solve for y prime. I prefer B over A because it's a lot nicer to look at actual numbers than variables then. So I'm going to go ahead and plug in 0, 0 right now. Okay, so let's see. In the first part, I'm going to get 1 divided by 1. Multiply by the second part, you're going to get, looks like it's going to be equal to 0 in this case, right? So let's see. Oh, that's a numerator. I'm sorry. Looks like it's going to be, 0. So that's just going to be plain old 0. Is equal to 1 over 1 multiplied by y prime. Okay. So cleaning it up once again, the left-hand side is just strictly equal to 0, and the right-hand side is just strictly equal to y prime. So there we go. Okay. And I guess if you want the equation of the tangent line, we can go ahead and plug in point 0, 0. So y minus 0 is equal to 0 times x minus 0. Or you could just plain old get y is equal to 0 then. All right, so hopefully this helps for you guys, and I hope